An op-amp-based second-order low-pass analog filter is shown here using an ideal op-amp. Let's figure out its frequency response and also its characteristics. In this case, we don't need even to figure out the frequency response to understand and identify this is a low-pass filter, because imagine if the frequency is really low, close to DC, so omega is nearly zero, or radian frequency. The steady-state impedances of these capacitors are inversely proportional to omega. They are 1 over JC omega. As a result of that, when omega goes nearly to zero, the steady-state impedances of these capacitors would go to infinity. As a result of that, these become open, these wires here, these connections. So in such scenario, at super low frequency, this voltage is directly connected to input positive terminal of op-amp, and there is no way for current to escape, because we are assuming this is an ideal op-amp. It means the input impedance is infinite as well. So there is no way for current to flow when we are talking about super low frequencies. Therefore, there is no current drop, or the current drop across R1 and R2 is negligible, as this V in appears exactly on positive terminal in such scenario. When we are saying this is open, C1 is open as well. And because this is an op-amp in complete buffer mode with a negative feedback enabled, whatever voltage appears here in this ideal op-amp scenario appears at the output as well. So in super low frequencies or close to DC, you can assume V in appears at the output directly. Basically, the gain of the system, VO over V in, is 1. In super high frequencies, for the same reason, the impedances being 1 over CS or 1 over JC omega, omega in denominator is super large. Therefore, you can assume that impedances for these capacitors approach zero. It means these are roughly short. So in high enough frequencies, the positive terminal is short at the ground. Since again this ideal op-amp is in buffer negative feedback, therefore whatever voltage appears here as positive terminal, which is zero, appears also on output at the output. So it means irrespective of V in applied for high enough frequencies, V out will be zero. So that's an indication that this system is not passing high frequency components and is only passing low frequency components. Therefore, it's a low pass filter. Okay, so now let's find the frequency response of this system. As said, since this ideal op-amp is in complete buffer mode or negative feedback, the negative input terminal is directly connected to the output. Whatever voltage is here at output is also at the positive terminal. So we can write it there that this voltage here is effectively V out. Okay, this voltage here is V out. Now, the voltage Vx here shown for this unknown node, there is just a voltage division between Vx and Vout as a function of impedances, as a function of R2 and 1 over C2S. So we can write it down. What I can write is Vx, again, these are function of S functions, so, or Laplace transform. We are using S domain impedance voltage division. So what we have is Vx should be equal to, or if it is more comfortable, we can say the other way. So we can say we know Vout is a voltage division starting from Vx, and that voltage division is 1 over C2S divided by 1 over C2S plus the R2. That's just a simple voltage division and times Vx. So if we just simplify this, what we get is this. We get 1 over 1 plus R2 C2S times Vx. And from here, we obtain that Vx is simply 1 plus R2 C2S times Vout. So I'm going to keep this as equation 1. Okay, I know this as a function of Vout. Now, at this node, what I can write is a simple KCL. current coming in should be equal to current going out. So at node Vx, I'm going to write KCL at node Vx. Okay, so what is that? Okay, so on one side, V in minus Vx divided by R1 is the current flowing this way. So I'm going to say Vn minus Vx divided by R1. That's the current flowing in. And let's say there is a current flowing out and current flowing out. So the sum of those two currents should be equal to this flowing, the current that is flowing in. Okay, so the good thing is about this current, I can just say it's Vx minus Vo divided by R2, or it's Vx divided by the sum of these two series impedances. So it's all right. I mean, I can just say Vx minus V out divided by R2, R2, and then plus this current, which is Vx minus V out divided by 1 over C1s. So Vx minus V out divided by 1 over C1s. Okay, so in this case, I can say Vn minus Vx. I'm going to use equation 1. So Vx is 1 plus R2 C2s V out, the whole thing divided by R1 is equal to Vx minus V out. So Vx is itself this V out times R2C2s. So when you subtract the V out of this guy, the only thing that remains is R2C2s times V out. So what I have is R2C2s times V out divided by R2. And obviously, one nice thing out of this is R2 cancel out with R2. So and Vx minus V out, I can just again do the same thing. So it becomes Vx minus V out, for the same reason I mentioned before, is R2C2s times V out. And then so what C1s would show up from denominator into numerator. So it becomes effectively R1, R2. Oh, I made a little. Okay, so it becomes R2, C1, C2, S2, V out. That is what we get. Okay, so the nice thing is now I can just multiply both sides of this equation with R1 to get rid of R1. So what we're going to get is Vn is equal to 1 plus R2 C2s. That's when I move this component or this term to the right side, and then plus R1 C2s plus R1 R2 C1 C2 S2 times V out. And finally, what we get is this V out divided by Vn, of course, as a S function, is equal to, I don't think we have enough space here, so maybe I just write it here. Okay, maybe I just write it here. So what's happening is is 1. Okay, so it's 1 divided by 1 plus, I can factor out C2s here, so it becomes R1 plus R2 times C2s plus R1 R2 C1 C2 S squared. That's it. This is my transfer function from input to output in S domain. So I'm gonna highlight this. This is effectively H of S, or transfer function for this second order analog filter using one op amp. Now, if you're interested, we can apply the values here. So R1, R2, 2 kilo ohm, and then C1 is 500 picofarad, and C2 is 500 picofarad as well. So if we do that, what we get is, okay, so we have 1 plus, R1 is 2K plus 2K, that's 4K, times C2. C2 is half a nanofarad. So 4 times half is 2, and you have 10 to the 3 because of resistors, and you have 10 to the minus 9, so you get 10 2 times or 10 to the negative 6 S plus 2 times 2 4K, we have meg, so that's 4 meg, and then C1 0.5, so it's 1 over 4 times 4 cancel out, so you have 10 to the 6 from resistors, and then you have 10 to the negative 18 from 2 caps multiplied. So that leaves you with 10 to the negative 12. And that's S2, S squared. Okay, so that's our transfer function for the given example here. And what we can do is, if you want, we can just go to, let's say, MATLAB and plot it. So I have already prepared a little bunch of lines on MATLAB code. Let's see if I can paste it here. Yes, great. Okay, so this is what you need to do effectively. So if you use this setup MATLAB command, which basically you define, what we are doing is we are finding and graphing the frequency response of this transfer function, which is the one that actually I have to change this. So here you have to change this to, let's say, 1e to the negative 12, and here you have to change this to 2e negative 6, and then correspondingly you have to change these guys, and you have to change this one. So this is the vector that contains the coefficients for denominator, and of course in your numerator in this transfer function you just have 1. That's why b, or the numerator coefficient vector, is just or is just 1. And then we are doing a log space in terms of defining omega on the x-axis for the plot, covering frequencies from 10 to the 0 to 10 to the 8 up to 100 megahertz. From 10 to the 0 is 1 hertz. And then we are just plotting the frequency response of this system by just using this A and B here and W, or omega. Okay, so with that in mind, let's just run it, and I'm just going to show the resulting frequency response here. So the resulting frequency response is, I'm going to just show it here. Okay, just bear me for a sec. There you go. This is the resulting frequency response. This is the resulting frequency response. If it allows me to, okay. All right, looks like I'm not able to paste it, but what I can do is I can actually do another trick which is image capture. Okay, yes. So this is what you get. Okay, so what is the significance of this? Well, it shows the magnitude response and phase response of this second order one op-amp based system. And you can see it's purely low pass from frequency of 1 radian per second up to frequency of 1 meg, roughly 1 meg. You can see that it is passing the incoming signal without a problem. And on the y-axis, you can see magnitude is 10 to the 0 or 1, basically gain of 1. And then 10 to the negative 1 is gain of 0.1, which effectively means 20 dB. So roughly up to close to 1 megaradian per second, radian per second. So you can see that it's um, it's roughly passing. I would say maybe you could argue that the 3 dB cutoff frequency for this low pass filter is on the order of um, I wouldn't be surprised if it is on the order of, let's say, 600 or so. Um, uh, I would say 600 kiloradian per second on that order. But it's easy to find it. It's basically the roots of this denominator. Um, so, and you can see the phase response as well. So as expected, because you have two poles in this system, because the denominator is a second order, as a result of that, you can observe two things. One, you can observe that in the in the part that it is dropping, the rate of drop for the magnitude is actually, as you can see, from 10 to the 6, which is 1 megaradian per second, to 10 to the 7, which is 10 megaradian per second. We are dropping by 40 dB. So it's 40 dB per decade drop. Decade meaning that 10 times increase in the frequency. Every 10 times increase in the frequency, you're dropping 40 dB. And that's because you're dealing with two poles located at the same position. And then phase the same thing. When you get to the point that you're 10 times, at least 10 times higher than the location of poles, you can see that the phase has changed by negative 180 degree. That's because per pole, the phase changes by negative 90. So you have two poles, you change by negative 180. Okay, I hope that this review of this simple op-amp based second order low pass filter is helpful.